For question B, we're using the same information that we're given in question A. So again, we're told that an elevator has a maximum capacity of 1,480 pounds or 10 passengers. We're going to assume the worst case scenario where the elevator is filled with 10 adult males. And we are going to, this time, find the probability that the sample of 10 randomly selected adult males has a mean weight greater than 148 pounds. So I really want you to see the difference between question B and question A. So take some time and go back and look at question A again, just so you can compare these two questions. In this specific question, I want to know what is the probability, right, that the mean weight, so the mean weight is represented by X bar. So notice the difference here. I'm not looking at an individual value X. I want to know the probability that X bar is going to be greater than 148 pounds. So right away, I hope you can see how different this question is from question A. So in this particular question, I want to know what is the probability that when 10 adult males hop on this elevator, that the average of their weight is going to be greater than 148 pounds. So I hope you can see that there are many different ways that we can pack an elevator with 10 adult males. They could all have different weights, they could all be the same weight, but I want to know if I were to randomly select 10 adult males, right, what is the probability that the average of their 10 weights is going to be more than 148 pounds? So to answer this question, I'm still going to use that probability distribution that looks like a bell-shaped curve, right? But now, this time, instead of using the distribution for weights of specific individual adult males, I'm going to look at a sampling distribution of sample mean weights, meaning that every single value under this curve doesn't represent an X value, but it represents an X bar value, where the X bar, so I'll write off to the side here, is the average weight of 10 random adult males. Okay, all right, so every time I take a group of 10 randomly selected adult males, I calculate their average, and that's what we call X bar. So if I repeat this process over and over again, every time I get another group of 10 adult males, right, I could potentially get a different average weight. And so we can actually plot those averages. And when we plot those averages, what you learn in section 6.3 when we were talking about sampling distributions is that the distribution of sample means is also normally distributed. So because it's normally distributed, I can draw that distribution in this way where it looks like a bell-shaped curve. So this tells us that if I were to randomly select 10 adult males and calculate the average of their weights, right, the mean of all those sample means actually, so the mean of all the sample means actually targets the population mean. And so this is the central limit theorem. By the central limit theorem, we say that the mean of sample means equals the population mean. So in this particular problem, the population mean is 189 pounds. So I can also use that same population mean for this distribution. So at the center here, I can also mark it as 189 pounds. The central limit theorem the central limit theorem also tells us that the standard deviation of the sample mean, so the standard deviation of sample means, is approximately the population standard deviation divided by the square root of n. So here, instead of using the population standard deviation of 39 pounds, I would use 39 pounds divided by the square root of 10. So this is the key difference here, right, between question B and question A. So again, to answer this question, what is the probability that the average or the mean of 10 randomly selected adult males weighs more than 148 pounds? I can mark 148 pounds on my distribution and then highlight the area that represents that probability. So again, the area shaded in red represents the probability that an X bar, or a mean, for 10 randomly selected adults is greater than 148 pounds. So I'm going to use the calculator method here. And on the calculator, because of the central limit theorem, we're allowed to also use normal C, D, F. But because this question is dealing with a sample mean distribution, right? I'm going to put in first the lower limit, which is going to be 148 pounds. The upper limit is going to be a very large number. So you, once again, can use 1E99, or you can use a very large positive number like 999,999. I'm going to use 1E99, and according to the central limit theorem, since the mean of sample means is equal to the population mean, I can also use that same mean of 189 pounds. But again, the difference here is because I'm looking at a sample, a distribution of sample means, I cannot use just sigma. I have to use sigma divided by the square root of n. So here, I'm going to use 39 divided by the square root of 10. When you press enter, your calculator is going to give you a value that is going to be close to 0.999, which we might as well just round to 1, or that is approximately 100%. So in conclusion here, we would say that the probability that a sample of 10 randomly selected adult males having an average or mean weight greater than 148 pounds is almost most certainly going to happen, because the probability is close to 1 or 100%. And that makes sense because back in question A, we already said that approximately there's an 85% chance that one adult male is going to weigh more than 148 pounds. So if now you put 10 of them together and you average it out, that's going to be a pretty high chance that that's going to happen, right? So I hope you can see, again, the difference between question B, where we're looking at a sampling distribution of sample means, versus question A, where you're just looking at the distribution of one variable, which is the male weights.